Let's take a look at how to find the surface area of a, well, three-dimensional surface. So let's draw a quick picture here. So let's say we have some function up here. Now let's draw just an easy kind of shape like that. And we wanted to find the surface area above that over some region R. So let's call that some region R there. So the idea here is for every single little square down here or rectangle that you would get, that would map up to some spot on this surface. So for every point there would map up to the z value here, and you would get some other shape. So let's call this our function of x and y. So how could we find out what the entire surface area is? Well, we would find the area of one of those little pieces and add them up across the entire region. So if you think about this little rectangle that's down here in the xy plane, drawing a little bit bigger, it would have a little piece of dx and a little dy to give us a small piece of area in the region. But we want to figure out what that ends up being when it gets mapped up here to the top. Well, it's kind of the idea. Pick some like arbitrary point in the middle there. And again, I got to draw this bigger than what it is. We would draw an infinitely small tangent plane right there. So act like the red part is tangent to the surface. Now, as long as these things are small enough, that means the area of this tangent plane right here would approximate the area of that little piece of surface. Now, I didn't draw them to the same scale just so you can kind of see what I meant by the tangent plane. So the idea is, how can I find the area of this? Well, this shape right here would be a parallelogram. And way back in the first chapter we did, we saw that we could find the area of a parallelogram by doing the magnitude of the cross product of two vectors that joined at a point. So kind of in this picture here, if one of those was u and one of those was v, creates a vertex here, then that would give us the area of the parallelogram. So can I find two vectors up here, u and v, for this particular shape? Well, we're going to break that shape down into kind of two directions so you can see what it's looking like. So let's say that the red shape looks something like this in the x direction. So over here we'd have a piece of dx, and on this side, now this isn't flat in the xy plane like this one is. This one's tilted a little bit, which means you'd have some in the x direction, but there'd also be some tilt in the z direction. So if I wanted to call this my vector u, so to speak, if I wanted to make that the vector, what would that vector be? Well, u would be the vector dx, no dy, and dz. The problem is I don't want things in terms of z because the way that this is written, x and y are my independent variables. So I want this in terms of my independent variable. So what would dz be? Well, since we're moving in this direction, dz is the rate of change in the x direction, dx, right? And you can see the dx's would cancel here. So another way to write this would be dx 0 and, well, since z is defined as f, right? This would just be f sub x dx. Okay, so there's a vector u, and kind of the way that we kind of have this picture drawn, I know it's a little weird to look at it like this, but we could say that this side there was u, or the opposite side. Now the other one, v, works almost exactly the same way. I'm even going to draw it kind of in the same orientation. But this one would lie along the dy direction, so that's kind of like this side here. This is going to be our v here. Now again, it's no longer flat in the xy plane, so when that goes up here, it gets a z component, dz. So we could say that v here is none in the x direction, dy, and dz. Now the same argument as before, I want this in terms of all my independent variables. Now since z's related to y in this case, we could see that dz, dy would tell us the change in the z when we're moving in the y direction. Now again, another way to write that would just be f sub y dy. All right, let's get rid of this picture now, just so we can kind of see. So if I find the area of this parallelogram, that red parallelogram, that will give me a very, very small piece of the surface area. So I'm going to do it as DSA. A very, very small piece of the surface area will be the magnitude of U cross V, or that's the area, that little tiny tangent plane at that surface. So we got to do the cross product. So let's go ahead and do U cross V. Let's move it over here so we can kind of put the pieces together. We'll need that in a second. So just U cross V, I, J, K. U was dx0 and f sub x dx. dy was 0, dy, and f sub y, dy. Okay, so if we do the cross product here, let's see, in the I direction, that's going to be 0, f sub x dy dx in the I direction, minus in the y direction, that's going to be f sub y dy dx, and minus 0 in the j direction, plus in the k direction, that's just going to be dy dx. Now, of course, it could be dx dy, I don't care. All right, so there is our cross product. So what do we need to do now? We need to do the magnitude of f sub x dy dx, negative f sub y dy dx, and just dy dx. Okay, of course, that's going to be the square root of each one of those squared. F sub y, f sub x dy dx squared, minus f sub y dy dx squared, plus dy dx squared. Now, if we notice, every single one of these has a dy dx. We can factor that out. Let's see. So this is going to be f sub x squared. Move that over just a little bit. Plus f sub y squared plus 1 dy dx squared. Now, since now that it's joined by multiplication, I can just take the square root of each piece. Now, I'm going to assume that a small piece of area, because that's what dy dx or dx dy represents, is a positive quantity, so I don't need absolute values on here. So this just ends up being, I'm just going to change the order of how we normally write it, f sub x squared plus f sub y squared dy dx, or generically 1 plus f sub x squared plus f sub y squared dA is what a very small piece of the surface area is. Okay, so this was the important result that we needed from here, which means if we want the entire surface area, all we'd have to do is add up all these very small pieces across this area. So the surface area will be equal to, well, since this is a area element, we got to integrate with respect to x and y, so we would do a double integral. The square root 1 plus f sub x squared plus f sub y squared dA over the region that we need to integrate. Okay, so it's a formula. Now, if you notice, this looks a heck of a lot like our arc length formula from Calc 1. Remember, arc length, little s, is equal to the integral of the square root of 1 plus y prime squared dx or dy, depending on which way you go. So in this case, notice it's just we had to do both derivatives. So one way to think about surface area is just arc length in 2 dimensions. Now, unfortunately, just like before, since this is somewhat like an arc length integral, most of the time it's incredibly hard, if not impossible, to do. So let's try one quick example of this using the formula. And I believe this is a lot like the example we did for polar, so that's going to be a good callback. So let's say find the surface area of f of x and y. I think it was something like this. Let's do 25 minus x squared minus y squared above x squared plus y squared is less than or equal to 9. Okay, so the idea here again is kind of like the picture that we drew for the polar thing. We have a semicircle, or a half of a sphere here, and we want to go above some region down here. Now this is just going to be above a circle, so what we're looking for is this kind of top here. So what it kind of looks like, think about it as the top of a deodorant thing, right? You got a sphere with a dome on the top. So what's the surface area of that dome? Okay, so using our formula, let's see if we can find all the pieces first. So our region here is going to be this region down there. That's what we're going to integrate across. Since that region is a circle of radius 3, I'm already thinking polar is probably a good idea by the time we get to the end of this. So this is our region R. All right, but to do this, we're going to have to find f sub x and f sub y. So let's go ahead and do that real quick. F sub x would be the derivative of this with respect to x. So, of course, we got to do the derivative of the outside. So bring down the power, copy the inside, take 1 away from the power, multiplied by the derivative of the inside. So we're taking the derivative of the inside with respect to x, which is just negative 2x. So f sub y is going to be, excuse me, negative x over square root of 25 minus x squared minus y squared. Oop, f sub x. F sub y, well, it's going to be almost the same thing. Bring down the power, copy the inside, take 1 away from the power, multiply by the derivative of the inside. The derivative of the inside with respect to y is negative 2y. So f sub y is going to be negative y over the square root of 25 minus x squared minus y squared. Okay, so now we need to plug it into our formula. So let's go ahead and just do this on the inside. The inside, remember, was the square root of 1 plus f sub x squared plus f sub y squared. So let's see if we can simplify this. This is going to be messy. So this is going to be the square root of 1 plus f sub x, that's this, negative x over square root 25 minus x squared minus y squared squared plus negative y over square root x 25 minus x squared minus y squared squared. Now we're going to have to integrate this, so we're probably going to want to try to clean this up quite a bit. So I'm going to squeeze one more line down here. Hopefully you guys can still see it. Of course, that's 1 plus x over 25 minus x squared minus y squared plus y squared over 25 minus x squared minus y squared. All right, if we get a common denominator, I'm going to skip a step here. The common denominator is, of course, the 25 minus x squared minus y squared. And when we add that together on the top, the x squareds and y squareds are going to go away. So this actually all simplifies to the square root of 25 over 25 minus x squared minus y squared. Right, just get a common denominator and add them all together, and this is what you should get. Which, of course, the square root of the top over the square root of the bottom gives us 25 minus x squared minus y squared. All right, so that's simplified quite a bit. So now what we're actually aiming for is we need to do the double integral over our region R of, well, 5's a constant. 1 over 25 minus x squared minus y squared dA. Okay, so that's the integral we're stuck with doing. Since we're integrating over this region R, and this region R is a circle, and I see I kind of have this x squared plus y squared thing going on there, I'm thinking polar might be a really, really good idea. So I'm going to go ahead and erase all of this and bring what we have over here. I might leave that right there for a second. So let's do 5 double integral over our region. Now if I convert this to polar, this is going to be the square root of 25 minus r squared. And that's going to be our r squared. And dA in polar is r dr d theta. So what are the bounds for the region here? Well, r is always going to run from 0 out to that circle, and that circle has a radius of 3, so this can go from 0 to 3. And to sweep out that entire region, theta is going to have to go from 0 to 2 pi. Okay, so 0 to 2 pi, 0 to 3, and I'm going to rewrite this as 25 minus r squared to the negative 1/2 r dr d theta. Okay, to integrate this is a very straightforward u du substitution. We would let that stuff be u, which is 25 minus r squared, so du is just negative 2r dr. Same kind of thing we did last time when we had an integral like this. Let's stick the negative 2 in there and bring a negative 2 out front. So what does this turn into? Well, let's get ourselves a little bit more room. This is really just the integral of u to the negative 1/2, right? This is u to the negative 1/2 du. So we would add 1 to that power and divide by that power. So if we add 1 to negative 1/2, we get positive 1/2. Multiply that, we would get a 2 times 5 over negative 2, the integral from 0 to 2 pi. This is 25 minus r squared to the positive 1/2, 0 to 3 theta. Right, u to the negative 1/2, add 1 to the power, divide by that power, and stuff. All right, so top endpoint minus bottom endpoint, what are we going to end up with here? Well, that's just going to be negative 5 on the one side, 0 to 2 pi. The top endpoint is going to give me 25 minus 9 to the 1/2 minus 25 to the 1/2 d theta. So 25 minus 9 is, what's that, 16? So square root of 16 minus the square root of 25, so 4 minus 5 is negative 1. So that's just 0 to 2 pi d theta. And of course, this integral here is just going to give us 2 pi, so that's 5 times 2 pi, or 10 pi. So the area of that surface above the circle of radius 3 on that hemisphere would be 10 pi something squared, feet squared, meter squared, miles squared. All right, so surface area, it is just a formula, and it is very much related to your arc length formula. Make sure you know how to apply it, but most of the time the integral is going to be really tricky unless they're kind of like this one, kind of made to work.